My name is Daniel Hart, and welcome to my final project for the course EGR 214, Numerical Methods for Engineers, taught by instructor Dr. Hans Chapman at Cape Fear Community College. I'll be doing a presentation on the application and use of MatLab to calculate double integrals. The related course for this topic is Calculus 3 and can be found in section 15.1 of the required text for this course. These are some related theorems that can be applied to calculate double integrals. Here we can see Fubini's theorem in its first and second form, its first form allowing us to calculate the volume under a rectangular region, and its second to calculate volume over bounded non-rectangular regions. Fubini's theorem states that double integrals of any continuous function over a rectangle can be calculated as an integrated integral. For this presentation, I'll be focusing on the first form, but felt the need to show how Fubini's theorem can be applied over any irregular surface to calculate volumes as well. The difference being that we must integrate over the function given as the bounds of the non-rectangular surface instead of bounds defined by a combination of a linear path with respect to rectangular bounds of one variable or rectangular bounds by both variables. We see that the total volume can be found by integrating twice over these values, and in Fubini's first form, we can note that the order of integration doesn't matter as long as the integration is performed properly with respect to each variable and its bounds. For our first example, we are asked to calculate the volume of the region bounded by the elliptical paraboloid shown in the figure to the right, bounded by x and y minimums of 0 and x and y maximums of 1 and 2 respectively. We first integrate the function with respect to the y variable over its bounds, and then integrate with respect to x and its bounds, finding our total volume under the paraboloid to equal 86 over 3, or 28.67 cubic units. For writing our MATLAB script to calculate the same volume, we first use the sims function to define x and y as variables. We then ask the user to input the function we will integrate over. It is important to note that when inputting a function in MATLAB, we must call over what variables the function is in respect to by using syntax @ and in quotations, in this case, x, y. This saves our function to be used later in our final calculation. We then use xmin, xmax, ymin, and ymax to define our bounds with respect to our minimum and maximum values for each variable. As our script is written, these names are now defined as bounds once we are asked, and input them into our workspace for our script. Finally, using the integral2 function in MATLAB, we call our saved equation all our minimum and maximum values placed in the correct order to calculate the volume under the paraboloid. This function is very useful in this way and can be altered over any number of integrals by changing the number after the integral name. As stated, we use integral2 to calculate the double integral, finding the volume under the elliptical paraboloid equation to be 28.67 units, which we can see to be the same solution as our previous analytical solution. Here, we see a similar example, asking us to find the volume of the region bounded by the paraboloid x squared plus y squared, with bounds of x and y minimums -1 and maximums of 1. We apply Fubini's theorem to calculate the double integral, in this case, first by integrating with respect to the x variable over its bounds, and using our resulting equation to integrate with respect to the y variable and its bounds. Our final solution being 2.67 cubic units, the volume under our paraboloid. As seen in the command window of our MATLAB program, we can use the same script again to calculate our double integral in a quicker and more efficient way, simply by inputting our function and our maximum and minimum values with respect to each variable. As long as correct syntax is utilized, we can see this MATLAB script is a great tool to quickly find the volume under a paraboloid or any multivariable function, as long as its bounds are properly defined. We see the total volume is again the same as the volume we found in our analytical solution. To review, upon the completion of this project, it further solidified what I've already concluded from this course, that MATLAB is an amazing tool to calculate tedious mathematical problems in a fraction of the time compared to finding analytical solutions. I also learned that syntax was very important in the creation of properly functioning scripts, and through some trial, error, and further research, was able to find the solutions to problems I had early on in the code typing process. Finally, I learned more about double integrals, the theorems that allowed us to analytically calculate them in ways that I displayed, and the many applications they have, such as calculating volumes of known curved surfaces, and being an important step to find mass and flux densities for different bodies, such as reservoirs and other non-solid irregular planes, areas, or spaces. Overall, I believe this project has helped further gain valuable knowledge about MATLAB and its many uses, and why it can help us as engineers to more effectively and efficiently solve problems. I hope you enjoyed, and thank you for listening.